Good morning and good evening, everyone. I'm Helena Ribera, and I'm a postdoctoral researcher at Northwestern University. Before starting the talk, I want to thank the NSF for the Early Career Travel Award, and I also want to thank the Center for Optimization and Statistical Learning at Northwestern University for partially funding this research. And so in today's talk, I'm going to present a method that is able to perform sparse model selection in chaotic systems when there are hidden variables. And so the first thing that I'm going to do is I'm going to introduce the problem formulation, so we all know what is the problem that I'm trying to solve. Secondly, I'm going to show you that the problem that we're trying to solve is rather difficult and which are the techniques that we use to overcome said difficulties. And finally, I'm going to show you how our method performs given an experimental data set. And so we're going to consider a chaotic system of n state variables. And for the purpose of illustration, I'm only going to consider 3 state variables. And the thing is that we don't know which are the interactions between the state variables, but we do know that this system can be represented in the form of a system of ODEs. And so we have that this system of ODEs, each ODE depends on the state variables and on a set of parameters P. We also know that the chaotic system will have a time series for each state variable associated with it. And the thing usually that happens is that we don't have access to the state variables, rather we have access to some measurement of them. And so we are going to assume that we do know the relationship between state variables and measurements given by H. And for the duration of the talk, we're just going to consider that H represents some measurement noise. It is often the case as well that we do not have access to all the state variables, rather just a subset of it. So in this case, I'm considering a system of 3 variables, and I'm only considering 2 measurements. And the question that we're trying to answer is, given the time series of the measurements, can we recover the form of the ODE? That is, can we find the governing equations of this dynamical system? And so first, I'm going to introduce this function little f, which is obtained by discretizing time over here. And the thing that f does is it sends us from the state variable at time n to the state variable at time n plus 1. And this little f only depends on the state variable at the state variables at the current time point and the parameter p's, and implicitly also to the form of f. So little f would send us from this time point to this time point, this time point to this time point, and so on and so forth. And so, as I said before, we do not know the driving mechanisms of the system, but what we can do is we can create a library of functions, here denoted thetas, and use them as candidate functions to describe the dynamics of our system. So one of the assumptions here is that the thetas are linear and only dependent on the state variables, but there is really no constraint on it. But this is just what we're going to consider for the duration of the talk. And so what I'm going to do is I'm going to put a parameter p in front of each of these candidate functions. And then the goal is to find which p's are 0 and which p's are non-zero. So you can imagine that if I find that this p is 0, then it means that this candidate function here, theta1, is not needed to describe the dynamics of my system. On the other hand, if I pick this term here to be non-zero, then it means that this function here, theta2, is needed to describe the dynamics of our system. And so the way that I'm looking for this set of parameters p is to have the most of them to be 0, but still be able to capture the dynamics of my chaotic system. And so that means that I'm looking for a solution of p that is sparse. And at the end of the day, to solve this problem, what we have to do is minimize the negative log likelihood, which is this function here, a, that I'm going to call either the action or the cost function. And so we're minimizing over all the state variables at each time point and over the parameters p. And so this function has 3 distinct terms, and I'm going to go one by one to go briefly over the assumptions that are made here. And so the first assumption in the first term, which is called the measurement error, is that there's no correlation between errors in measuring different quantities at varying time points, and also that the measurements have uncorrelated Gaussian error. This last assumption, if you do know that this is not true for your system, can be changed in this function. But for the rest of the talk, this is what we're going to assume. Secondly, we have here this term, which is called the model error. And there are two assumptions here. One is that the next time point only depends on the previous point. And we see here our little f that we described before. And then in principle, this would be a delta function if there was no error in the model. But we allow to be some error in the model by widening this delta function. And then we obtain this term. Finally, we have the term that's going to control how sparse is P. And the way that it has this form is because we've assumed a Laplace distribution on the parameters P. And so we have here lambda, which is the sparsity knob that is going to basically control how many of these P's are 0. And so you can imagine that if you're minimizing this, the bigger this is, the more parameters are going to be forced to 0, and also the other way around. So just to recap what I've just said in this slide, the question that we're trying to answer is, can we recover the governing equations of a chaotic system given some measurements of some of the state variables, but not all? And the answer is that yes, we can. And the way that we're going to do this is by minimizing this cost function. Okay, so we want to minimize this function here. And what does this look like? So here is a representative cost function in 2 dimensions. So that'd be varying 2 parameters in the parameter vector P. And we see that this is a highly non-convex function. And therefore, trying to find the global minimum of it, it's going to be a very hard task. So we need to use some sort of technique to overcome this problem. And we're going to use a data simulation technique called variational annealing, presented in this paper here. And in this slide, I'm going to go over through what the variational annealing method really is. And so first of all, we're going to forget about this part here for a second, and we're going to consider only the error in the measurement and in the model. And so variational annealing, like key point is to use this parameter as to slowly enforce the model. And so first, if we assume that RF is 0, it means that this function has no information whatsoever about the model. And this is a very convex function that has for solution to the measured variables, the measurements. But if you try to minimize this over the whole problem, that is over the unmeasured states and the parameters on these variables, the solution is very degenerate. And so this is no good. And so the key of variational annealing is to start with RF being very, very small. That is that we're enforcing the model very little, and then we add some complexity into the landscape. And so the first step is to find a minima here using whatever optimizer. And the key is going to be to slowly increase RF in a way that the landscape of the function changes smoothly enough that we're able to track a minima. And so, for example, if we pick, if in the first step where RF is very, very small, we find this minima, on the next step of variational annealing, we're going to start the search at this point. And because the cost function is changing so smoothly, we're going to be able to stay again in this minima, that is to track it. And we're going to do this so on and so forth until we finally get to the last step of variational annealing, which corresponds to when we have fully enforced the model. And in like a few minutes, I'm going to explain really what that is. But yeah, the point is that we're able to track a minima. And in this case, for example, from starting here, we would find this minima. Now, if we had started in this point, because that can be the case, variational annealing would have helped track this minima. And for example, we would have gone from here to here and to finally say here, for example. And so the thing is that if we're looking for the global minima, we're going to need more than one initialization to the unmeasured state variables and parameters to be able to fully explore the landscape here. And so like to be able to find all the interesting minimas that we can find. So if we're looking at this more in an algorithm kind of way, we have that we did an initialization. And as I said, the state variables that are observed are going to be matched to the measurements, and the unobserved variables are just going to be initialized at random. And the parameter P, since we know that a lot of these terms are going to be 0, we initialize it, all of them at 0. And so we start with RF being very small, and we solve this problem using an interior point optimizer. This gives us a solution for the time series of the measured and unmeasured state variables and also the parameters. And then we increase RF using this criteria here, and then we solve again this problem, and the starting point is going to be the previous solution, and so on and so forth, until we reach to the RF maximum. That is when the model is fully enforced. And here we have to do a bunch of initializations, as I said, to be able to ensure that we fully explore the landscape of the function and that we ensure that the global minima is found. So what does this look like? So here I'm showing a plot of 500 different initializations, and here on the x-axis I'm showing the strength of the model enforcement, and here I'm showing you the action value. And so, for example, we see that there's in blue this path that means that we ended in this global minimum. But then here we also see a bunch of other like endpoints in terms of minima found. And so in dark gray, for example, here, and once you get here, they're very hard to distinguish, but these are minimas that are found that are very close to the global minima one, but not quite. And so this would be like in a very sketch manner, the ones here. And then we have a bunch of minima found that are in light gray that would represent minimas that are found that its value is very far from the global minima value. And this would represent in this sketch way the points up here. And so, you know, we've done a bunch of different initializations for the unmeasured variables, and we found that for some of them we get to the global minima, and that for some of them we don't. And that's the reason why you need to do more than one initialization. Okay, so far I've solved the problem of having this Helena convex cost function, but we've not done anything regarding this part of the cost function that we have to minimize. And so before getting into how we solve this, I want to show you kind of what the cost function looks like as we increase lambda. And so, for example, for a generic parameter pkj and one value of lambda, we have that the global minima falls to -1. And so that would mean that the associated library function to this term would be deemed necessary to describe the dynamics of our system. If we increase lambda more, we still see that this parameter pkj is now -0.5 more or less, and still the function associated with it is necessary to describe the dynamics of our system. But for a lambda big enough, we put this parameter pkj to 0, meaning that the function associated with it is no longer necessary. And so the question is like, which lambda is going to produce the sparsest model possible that describes the dynamic of our system? And of course, we don't know that a priori. And so we're going to have to do a search among all possible lambda values to find all the candidate models that describe the dynamics of our system. And so, you know, given the setup that I've presented already for the variational annealing, is there any way that we can use it to kind of solve the problem once we have this penalty term here? And the answer is yes. So we know that one solution to the L1 problem is to minimize this first part and then hard threshold the parameter vector. And so in this setup, what we can do is add a hard threshold part. And so for every step of the variational annealing, the output of the parameters P is going to be hard thresholded by the lambda given. And so any value in this parameter vector that is smaller than its absolute value to lambda is going to be set to 0. And then this is going to serve as my initial condition for the next step of variational annealing, and so on and so forth until the function plateaus. And this will give me a model that not only depends on lambda, but it also depends on the initialization n. So for each lambda, I will have a bunch of models, and then I just do a sweep for a certain amount of lambdas. And so what this looks like is something like this. So we have here at the bottom lambda, and here we have the number of active terms on the model found. And so for one particular lambda, say lambda 4, we have a model that has 6 terms, a model that has 7 terms, a model that has 8 terms, and so on and so forth, until we have a model that has 23 terms on it. And then, of course, each lambda will produce different models, but we see a trend that for bigger lambdas, as is expected, the models start to have less active terms because we're pushing more of them to be 0. And here the color code is the same as in the previous slide. So in light gray, we have models that ended up having a high cost function. In dark gray, models that have a low cost function. And in blue, we have models that have the lowest, so the global minimum of the process. And the question among all these candidate models that, for example, in the case that this graph came from, all the possible models that you can construct from the library that we use was something along the lines of 10 to the 9 different models. And here only represented are 170. So we down selected a lot the possible candidates that can describe our dynamics, but this is still like a big chunk to choose from. And so other criteria need to be used to pick which is the best one. So things can be AIC, it can be BIC, it can be plotting a Pareto front. And so that depends, the thing that you use to pick the best model will depend a lot on the data that you have. But this is the big picture on how this is done. So this is how we find candidate models to describe dynamics from a dynamical system when there are hidden variables present. Okay, so finally, I can go to show the experimental results that we got using our method. And so in this paper here, they presented this electrical circuit. And in the paper, they measured voltages on X and Z. And they didn't measure voltages across the Y point. And so the time series of this experimental data set looks something like this. So we have this for X, this for Z, and we have nothing for Y. Now, if we were to plot a time delay embedding on these two variables, we obtain something that looks a lot like the Lorentz attractor. And looking at the paper, the equations that they derive for the voltages in X, Y, and Z look like the Lorentz system, except for that the parameter here, here, and here is not set to 1 as it is in the classical formulation, but other than that, we have the exact same structure. And so, we have a chaotic system for which we have to measure variables out of 3. And so this is the perfect data set to try to use our method on. So the thing that we need to use our method is first the time series of the measurements, which are these ones that we use that have 501 time points. And then we need a library of candidate functions. And so we picked all monomials up to degree 2 and 3 variables. And then we constructed, as I showed in the first slide, the generic function for X, Y, and Z. And so we used our method, and at the end of the day, what we had is we had 25 candidate models that were able to explain this data. And the thing is that in this kind of library, what you have is you have 10 to the 9 possible models. And so we reduced very significantly the amount of models that we have to test and validate. No? And so we used a certain amount of time segments from the original time series to validate these models, and we plotted the Pareto front to do that. And so here we have the number of active terms, and here we have the average error. So first, if we look at the inset, we see that models with 4 and 5 active terms have such high average error that they no longer appear here in the smaller picture. And then we have that the difference in error between the model that has 6 active terms and the model that has 12 active terms is very, very small. So what I decided to do is I picked the models at each number of active terms, the ones that had the smaller error, and I just went to look at what they look like. So the first thing worth mentioning is that we actually are able to retrieve the system that is proposed in the paper to explain the circuit. Okay, so we found this, which is the one that has lowest error for 7 terms. Okay, The thing is, though, that for the remaining 6 models, the error is very similar between all of them. The manifolds look extremely alike, and the Lyapunov time of each of these systems is very, very similar. And so what we found is that even though we were able to select this model, which is the one proposed in the paper, we found 6 other possible models that describe the data very well. And now the question is, is this model the actual one to represent the data, or is it not? And the answer is we don't know, because we don't have access to the experimental setup. So given the experimental setup, we could design other experiments to determine which one of these models is the actual one that describes the data. But with the information so far, we cannot pick any of those as to be the best one. But all of them are parsimonious models that describe the data, which is the goal of our method anyway. And just to finally just illustrate you how similar these models really are, here I'm plotting time, and here, each of the variables, and vertical lines denote the Lyapunov time. And so we see that, these systems are really indistinguishable between themselves up to a Lyapunov time. And this is how much you can expect to predict a chaotic system anyway. So it doesn't make sense to look further than this. But yeah, the important thing is that 1, we found the model suggested in the paper, and 2, all of these models are sparse and are able to capture the data, which is a success on our method. So what have we learned today? So in today's talk, I've presented a method for model selection with hidden variables. And to do that, we've combined a data simulation technique called variational annealing with sparse model selection via hard thresholding. What we were able to do is that we successfully recovered the model for the Lorentz system with 1 hidden variables from a set of experimental data. And I didn't have time to talk about this today, but we also studied how noise and manifold sampling affect the model identification problem using a set of synthetic data. And just to finish off, I'm going to leave you here with a link to the archive paper where all the details can be found.